All right, continuing on with 13.4, Redox Stoichiometry. This is part 3 of the lesson. We're going to take a look at example number 2. This one is an actual titration. It is the sample problem from page 597 in your textbook if you're looking for another explanation of the particular concept. So here we go. We're trying to determine the concentration of potassium permanganate solution when it is titrated with an acidic tin 2 chloride solution. So we have our titration here. Again, remember your titrations are about precision, so we have multiple trials. The title is always descriptive. We have a known volume of a concentrated tin 2 chloride solution, so we know everything about tin 2 chloride. Because it's its fixed volume here, I know that this is the limiting reagent and therefore the sample. Neat, huh? All right, we're going to titrate this with potassium permanganate. There are two things that we're trying to find out. One is its concentration, and two, what volume do we actually use to neutralize or completely react our limiting reagent. For this, we had something known as best average volume. Remember, this was a minimum of 3 trials that were no different by plus or minus 0.1 mil. When you take a look at some of these values here, you can see that we had an overshoot trial. This was our approximate. We do that one quickly. You'll remember that from the video. And then we have 3 that are done with much more precision. We can see that these 3 have no greater difference than a plus or minus 0.1 mil. All right? Or a total range of 0.2 mils if you prefer it that way. But 16.7, 16.8, all right, 16.8 and 0.7, this is 0.1 lower, this is 0.1 higher, so these fit. Add the 3 together, divide by 3, and you get 16.8 mils as your best average volume of titrant to neutralize the sample. Hope that makes sense. But before we go any further with this, we still need a balanced chemical equation. For that, we got to go to our entities method, and so we should take a look at all of the entities that can exist in this particular problem. Potassium permanganate, that's an ionic solution, so we will end up with K plus ions. Your permanganate, MnO4, 1 minus ion. We have a tin 2 chloride solution, so we have SN2 plus. We have chloride. It is acidic, so I know I have H plus, and I can't forget about the liquid water used to make these solutions. All right, we can kind of put the data to rest for a little bit. We've got to figure out what our balanced chemical equation is. So for this one, there are 5 OAs and 4 RAs. I would encourage you to pause the video, break out your reduction half reaction table, and try to find them. All right? Give that a shot. All right, I'll see you back here in a few minutes, and then we can continue on with this one. Welcome back. All right, we've got our OAs and our RAs. Potassium you found as an OA. Permanganate on its own wasn't, but acidified permanganate was. We have tin 2, which we saw in an earlier lesson as a disproportionation possibility. It is both OA and RA, or at least can be. And of course we have chloride. We saw that in the last example. Water is also a disproportionation candidate. And we have one more, the chloride water RA. So there's your, oh, I'm missing one. I forgot about H plus. All right, there's your 5 OAs and your 4 OAs, or RAs. Oh man, alphabet's killing me today. So now that we have these, we have to identify the strongest. Look out of these 5, which is the highest on the left-hand side. It's pretty easy to tell. It is going to be your acidified permanganate. It's sitting way up near the top, so there's your SOA. We take a look at SRA. Tin plays a role, and there we go. It is not disproportionation because it's not both SOA and SRA. So now we need to come up with our 2 half reactions. So remember that your SOA undergoes reduction, and as your SOA undergoes reduction, we're going to copy this rather complex looking one from the reduction half reaction table. But you have MnO4 minus reacting with 8 hydrogen ions and gaining 5 electrons to form manganese 2 plus and 4 waters. For our SRA, as we continue looking at that one, we have our oxidation half reaction. This one's much more simplified, but you have tin 2 plus. You're going to lose 2 electrons and form SN4 plus in its wake. You've now successfully got your redox reaction. The only thing we have to do is make sure is that electrons gained are equal to the electrons lost, and unfortunately they are not. 5 and 2, the lowest common multiple here would be 10, and so I multiply my reduction half reaction by 2 and my oxidation by 5. That would equate my electrons, and now I can write my balanced redox reaction. So 2 MnO4 plus 16 hydrogens plus 5 tin 2 pluses gives me 2 manganese 2 plus, 8 waters, and 5 tin 4 plus. All right. Now we have our balanced redox reaction. We can finally start to apply some stoichiometry. So we go back and we're going to follow that column-based idea about organizing our information. With this one then, we look for the information that we have about our limiting reagent here. We have 10 mils of a 0.05 mole per liter tin 2 chloride solution. We found out chloride didn't participate, so really we're just looking at the tin 2. So we have 10 mils of this, and we know its concentration is 0.0500 moles per liter. Let's look at our excess reagent now. We were trying to figure out a few things. We were looking for the concentration of our potassium permanganate, and we know that it took on average 16.8 mils to do this. So we find out again potassium was a spectator, it did not play a role, so we still apply this to our permanganate, and so you have 16.8 mils, and we are looking for this concentration. So the only difference between this one and the last example that we had was, one, we had a titration data table to infer a best average volume, and two, we're looking for a concentration rather than a mass. That's it. So now we can do our stoichiometry. We have information about our tin 2. We know we're looking for a concentration at the end, so why not start with concentration to begin with, and that way our units will automatically work out. So we now have 0.0500 moles per liter of tin 2 plus. Again, we were looking for just moles, so while we would have 0.05 moles in every 1 liter, we can see that we have way less than a liter, so we have way less than 0.05 moles. Let's cancel out our liters before we do any of our stoichiometry. So 10.00 mils can go up top, and that will cancel out our liters. Remember in stoichiometry that any metric prefix does survive. If you hate this, convert 10 mils to liters and then put it into your factor label method. We now have millimoles of tin 2 plus. Because that is a mole quantity, we can now do the stoichiometry, which means we can use the mole ratio between tin and permanganate. Tin, I wrote this in here, I now know how to cancel it, and I'm looking for the amount of permanganate that was required to neutralize it. You can see it's 2 parts, or 2 moles permanganate, in order to completely neutralize and react 5 moles of tin 2 plus. This again is the only stoichiometry that we have in the equation. You now have millimoles of permanganate. Great. We can figure out a concentration once we start putting this in over a volume. So for this next part then, I just need to put in the volume of 16.8 mils. Down on the bottom, the numerator would be just 1, it can't be 0, and you can see that milli value that we had finally cancels out. And so moles per liter is the molar concentration of my permanganate that I have there. Run this through your calculator, and we get 0.01190, and this would be in moles per liter. There's your 3 digits, and so this would equal 0.0119 moles per liter of your permanganate solution. Hopefully that makes sense to you guys. I'm going to leave number 3 for you. Do it on your own. A solution will be coming to that one. Molly was going to offer you some encouragement and some cheers to get you through number 3, but painting a watermelon became, a picture of a watermelon became way more fun, and so she's abandoned me to you guys and the stoichiometry. Good luck with this, guys. Do your best with it, and we will finish off lesson on 13.4 as we get to the last video, which will be the example that we had, number 3. All right, and then of course there's the various assignment. Oh, I think we have a visitor. All right, so we've got some words of encouragement for you.
Good luck, guys. I hope you get the next question right. Good luck.
Me too. All right, there you go, guys. Have a great weekend.